We're now going to look at ray diagrams for a diverging lens. So the rules are actually exactly the same, but how we draw the rays is going to change. And the big reason it's going to change is that when you have a diverging lens, the focal length is negative. So our focal length is going to be -2. And the effect that's going to have is basically going to reverse which focal point we use when we're drawing our rays. So let's go ahead and read this question and we'll set it up and we'll do a ray diagram and then check our work with the equations. So a 1 centimeter tall object, so that's the height of the object, is 1 centimeter, is placed 4 centimeters in front of a diverging concave lens with a focal length of -2 centimeters. And the object distance is 4 centimeters. So again, I have a 1 centimeter tall object. I need to construct it exactly 4 centimeters out, which should be right at 2f. Remember, the first tick mark on either side is the focal point, and the second is the radius of curvature, also called 2f. So you need to very carefully now take a ruler and construct an object that is exactly 1 centimeter tall, 4 centimeters out from the lens line. So there we have our object, and now we're going ahead and we are going to draw the rays so that we can figure out where our image is going to be. Rule number 1, a ray drawn parallel to the principal axis is refracted through the focal point. Let's take a look. And now we're going to line up the point where that intersects with the lens line with the focal length on the left hand side. Now, no light is actually passing back off the lens. To indicate no light is bouncing off the lens, I actually have used a dotted line. There is actually light moving on the right side, so I do need to replace that with an arrow. And you can see I've replaced the right side there with an arrow. So you'll notice that this is different than the converging lens because initially we're using that focal point on the left side instead of the one on the right side. Rule number 2, a ray drawn through the focal point is refracted parallel. So this time for rule number 2, because it's diverging, we're actually going to use the focal point on the right hand side for our first rule. And so we're going to line our ruler up with the top of the object and the focal point on the right hand side. And we're just going to leave that like that. Now, what we should have done is refracted it parallel, so we have to make a few changes. I'll go over that first arrow in solid red. And now that that is solid red, when I get to the lens line, I actually have to bend. And I'm going to bend parallel to the principal axis. And then, of course, the last rule, a ray drawn to the vertex of a lens passes through unchanged, will be the same as in converging. Now that dotted line that I drew is actually needs to be erased in red because I just did that to show you how to line it up. So I've deleted that, and you'll see we actually will have to extend. It does not intersect on the right hand side. So what we have to do is extend our refracted rays backwards until they do meet. So I will extend this red ray back. And I need to change that green line again back to solid on the right side. And there you have a completed ray diagram. So you'll notice that we do not intersect on the real side because the rays diverge or move apart. So we had to extend each of these rays backward to the left side of the lens until they met. And they actually all met in exactly one spot. And I will draw the image in orange at that spot. And there you have it. There is our image. We connected where those rays intersected to the principal axis to get our image. So now let's just briefly compare it to our object. Is it bigger, smaller, or the same size? I would say it's certainly going to be smaller. Is it real or virtual? Well, it's not on the real side of the lens. And it's also upright, which essentially always corresponds with virtual. And of course, I gave away the last question, which was upright. We're now going to check this using the math, using the equation. So I'll delete those notes at the bottom so I can show you the math. So you need your equation, if I do, I die. So 1 over focal length equals 1 over object distance plus 1 over image distance. So we have 1 over -2. That negative sign is going to be a key here. 1 over 4 plus 1 over di. So you just have to solve for di. I highly recommend using your calculator and the inverse button. So -2 to the -1 minus 4 to the -1. Hit the -1 button to flip that fraction. And you get our image distance is -1.33 centimeters. And if we measure, that's exactly what this distance should be. So -1.33 centimeters is our image distance. That's because it's on the virtual side, in this case, the left side of the lens. So recall our magnification equation is hi-ho, negative d-do. So either of those fractions is equal to magnification. In this case, we're actually going to use the two fractions and set them equal to each other so we can solve for image height. So our object height in this case was 1, my favorite object height. And our image distance is -1.33, and our object distance was 4. So you're simply going to cross multiply and solve. And you get an image height of it's positive. So 0.3325. Remember to include that negative sign. So negative di, actually, I made a mistake here. This should have been positive because it should be the opposite of di. So the opposite of -1.33 is positive 1.33. So that's positive. And incidentally, that's also our magnification here because our object height was 1. So it's going to be 0.3325 times. And that's how you do a diverging lens. So essentially, use the focal point on the left first to bend the ray away, like we did with the green ray. Then you use the rule number 2, use the focal point on the right side, draw it to the lens line, and then go parallel. And then the third rule is the same as it would be even in converging mirrors, is as a ray passes through the vertex of a lens unchanged. And you'll see that that gives us those three diverging rays. Recall this is a diverging lens. So you can see ray 1, ray 2, and ray 3 were diverging, so we were not going to get an image on the right-hand side. So we had to extend those refracted rays back to the left-hand side until they met. And indeed, they all met at one spot, which is the location of our image. We then checked it with our equations, and we see that it matches up perfectly. So that is diverging lenses with ray diagrams and their equations. Thank you.